In this video, we want to describe the method for programming a linear regression. Now, this particular version is not going to be quite as sophisticated as something you might run into later down the line when you do more sophisticated linear regressions. But we will this will show you how to achieve the same result that Excel achieves. Okay, but the main limitation with Excel is this: when I have data and I plot it in Excel, the one thing that Excel does not know how to do when you plot things and just fit it with the trend line, it does not know how to take error bars into account in the calculations. But in situations where that is not important, then the algorithm it has works very well. And so suppose I have a function, not a function, but suppose that I've taken some physical data, okay? And this data is in a two-coordinate system, X and Y, for example. And whatever your data may be, it can be positions and times, it can be positions and velocities, times and velocities, it can be whatever physical quantities you like. It can be force and charge between two charged objects if you know the total charge on the objects and you measure the force. Whatever the case may be, right? You just have something in some units and you assume that the other variable you're measuring is a function of that something in some units. Okay, and if the data follow a more or less linear trend, that is always the first attack that physicists and generally scientists in general try to fit their data with. Is it simple enough to be described by a linear relationship? So that's why the linear fit is kind of, the most important fit for the physical sciences. Now, it's definitely not the only way to fit data, but when you don't know ahead of time, or when you don't have a good reason to think otherwise, this is usually the first attempt to model things. We see if they are fit with a linear line. Now, how do we do it? How would we build an algorithm to do it? So you'll notice that in generic data, right, generic real-world data generally does not fit very closely to a trend line. Real-world data, there's a lot of scatter in the data. So how do you handle this mathematically? How do you find what the parameters, the slope and the intercept of the red line here, that fits this data? How do you find the best slope and intercept? Well, one approach you can try is to say, wait a minute, I can draw all sorts of lines through here. I can draw lines with different slopes, right? There's no question that I can draw similar lines with similar slopes, and they all might be expected to be reasonable fits to the data. So how do I choose which one is which? And you can say, well, of all the possible slopes I can draw, what if I just took the difference between each data point and the slope? And I tried to find the line that had the smallest total amount of differences. And in principle, that would be okay with an exception, right? And that exception is when you take the difference between the line and the data point, like if I try to subtract the value of the trend from the value of the data point, I would get a magnitude of the blue line here, and the same thing would go for each individual data point. And if that's my only algorithm, take my data point and subtract the trend, then this would be a positive number, and this would be a negative number. This would be a positive number, and this would be a negative number, and this would be a positive number. Negative, negative, positive, negative. And so all I'm really doing in that case is my value would more or less be 0. And most of the lines that I could draw that would reasonably approximate the relationship in the data would also be very close to 0. So that's not a very rigorous way of doing things. So what we do is we do take the data point and subtract the value of the model at that point. Give me just a second here. But that's not the only thing we do. We then square it. So basically what we do is take an x position, or I'm sorry, not an x position, but a y position. Let's call this y0. Let's call this y1, y2, y3. So y0 has a value here, y1 has a value here, y2 has a value here, y3 has a value here, and so on. Okay? And the value of the model at those points is going to be here, 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 etc. Okay, so we're basically going to take the difference between our points, but then we're going to square them. So what we would do for this point right here is we would say, okay, take y0 and subtract the value of the function that I'm trying to model. Take the value of the function right there, and let's designate that by fun for function. Okay, so I take my actual data point minus the data point of my model, and I square it. And I do that for each term, and that makes everything positive. So now what I'm trying to do is find the line that makes the total difference between the square of my differences minimized. Okay, I want to find a function that minimizes the total sum when I add up all of these, right? So I would find this particular difference, then I would find this particular difference, y1 minus y1 fun, and I continue down the line for each data point, and I try to find the model that minimizes the sum of those squares. Okay, I want to minimize the sum of the squares of the differences between the data points. For short, we call this the least squares model. Okay, we call this the least squares model. And this is what Excel does. Let's suppose I have some generic data, and this is just generic XY data. And I plot it in Excel. I tell Excel I want to fit it with a trend line. It gives me all the options. I choose linear, and it gives me the slope, the intercept, and I can display the r squared value. And if I do a linest function, then it also gives me the statistics on the slope and the intercept. It gives me their errors. So I have a error on my slope of 0.0499. I would probably round that up to 0.05, and I would probably round my slope to 1.25, depending on the amount of precision I was able to carry based on the instrumentation of my instruments in the laboratory that I was collecting this with. But in any case, and the r-squared value 0.990464, rounded on the graph to 0.9905. Okay, so it's all well and good to try and minimize the differences or minimize the sum of the squares of the differences. But how does this actually work? What is the back end? What is Excel doing behind the scenes? So what we're going to do in Python today is we're going to write a routine that actually allows us to do this. Okay? And we'll calculate the slope, the intercept, the errors, and the r-squared value. Right? Now, before we go further, we have to look at the equations that do this, and there's going to be some notation. Okay? So, when you see this symbol, summation symbol x sub I is what's known as an index. Okay, I is what's known as an index. And what that means is, this means sum all of your x measurements. The I is my index, so this would be the same thing as x0 if I start my index at 0. And this is why I use 0, because Python starts its indexing at 0, and I'll show you what that means here shortly. But this means that this is the point x0, y0, right here. This would be the point x1, y1. This would be the point x2, y2, x3, y3, x4, y4, and so on. Okay? And so the i's are just the values of these indexes. So what this expression is telling you to do, it's telling you to take x0 and add it to x1 and add it to x2 until you've summed all of your x measurements. So what this is basically doing, this symbol right here, or this expression right here, is basically telling you to sum your x values. Okay? And likewise, summation symbol y sub I is telling me to do the same thing with my y values. And sum x sub I squared means I'm going to take each x element, starting with 0, square it, and then I'm going to add the results. So this would be the same as saying, okay, x squared, and then saying, okay, I'm going to take this, and I'm going to square it. This is x sub 0 squared. And then this would be x sub 1 squared, x sub 2 squared, and through the whole list, and then adding those up. Whoop. And then x times I, the summation of that means, let's take each x and I index for the same and multiply them. So x0 times y0, and then x1 times y1, and so on. And maybe I'll label this column Python index. We'll just call it index. And Python starts at 0, 1, 2, 3, 4, 5, 6. 7. So there's technically 8 elements, and Python starts its indexing at 0. Okay, 8 elements, 0 through 7. And then we want to summation this value. Okay. Now, to actually derive the equations that we're going to use requires some pretty sophisticated calculus, so we're not going to go there. We're just going to use the results. Okay, so there's 3 basic equations that we're going to use. And the first equation, these equations can be found, by the way, in most books on statistics or data analysis. This is a very standard result. And before, or in an effort to keep things from being too messy to the eye, we clean up a little bit of notation with this first expression. So we've just generically labeled it as delta, and I labeled it that way because that's how it's labeled in the book that I drew this from. But the delta value is given by n, and n is the total number of elements in your data set. In this case, we have 8. So n in our case is 8. And maybe I'll put that here. And delta is given by n times the sum of our x values squared, subtracted from the sum of our, I really should say this, the sum of the square of our x values. That's what this term is. The sum of the square of our x values minus the square of the sum of our x values. So once again, this expression is the same thing as this one. So that would be, the result would be that value right there. The sum of our the sum of the squares of our x values. And this expression means I'm going to sum up my x values and then square, whoops, I didn't want to do that. Means take the sum of our x values and then square it. So this is going to be equal to this squared. So the first value is going to be n, or 8 times 8 times 140, and we're going to subtract 784, right? So that is the delta value, and the delta value just appears in both equations for the slope and the intercept. So it's kind of factored out and cleans up notation. So your slope, once you have your delta value calculated, your slope can be calculated from this expression. So once again, we just take our number of elements times the square of the product of our x and y values, and we're going to subtract from that the product of the sum of our x values and the sum of our y values. So how do we do this in Python? Okay, so you'll notice I have already opened up a Python Baba editor, and I've imported my matplotlib.pyplot as plt, my numpy as np, and what I've done, and by the way, I'm going to pull this off to the side for just a moment, and I'm going to get rid of all these comments. All right. And we'll talk about what we're doing step by step. So for the first part, what I've done is I've created 2 arrays, right? And I've manually populated these. So before, I showed you how to use linspace and array to create arrays. But those create uniform arrays. right? But if you have experimental data, your data may not be uniform. So you can't just simply say, okay, I want to create an array from 0 to 500 with 1,000 elements. Okay, linspace is great for that. But if you have physical data to plug in, that's not the way to go. So here I've manually created my arrays, and what you do to specify a list of numbers as an array, I've imported numpy as np, so I have to put the np dot here, and I type array and then parenthesis bracket, fill in your elements separated by a comma, close your brackets, close your parenthesis. And that is all there is to it. All right. So now let's actually code the expression for delta here. Whoops. Okay. I want to be over here. So delta. All right. Before we do that, I'll show you one more thing. We know that there are 8 elements in this list, and actually it'll behoove us to go through before I define this just one thing, actually 2 things. So as I've mentioned, the Python starts its indexing at 0. So what if I wanted to just print the first element, or I really should say is the 0th element in this X array? What I would do is say print X, and Python now knows that X is an array because that's what I have bound that variable to. I have bound X to an array, and the elements of an array are given as brackets. So if I want the 0th element of my array, it should print 0.0. Okay. If I want the 0th element of my Y array, now this should print 1.1. If I want the 0, 1, 2, 3, if I want the 3rd element of my Y array, this should print 4.5. And sure enough, okay? So this is how you can call an individual element out of an array and inspect what that element is if you need to, right? And of course, the 7th will be 9.6. There we go. N in my calculations over here represents the total number of elements. In this case, N would be 8. 1, 2, 3, 4, 5, 6, 7, 8, right? And so the way I can do that, I can bind a variable N to that number, even if I don't know what that number is. Okay, so if I have a really big data set and I don't know how many data points there are, but I still want to do this, I can find N very, very quickly by the length function. So the length function is len for length, and then the list or array that I want to find the length of. So N equaling len x, if I print N, this should give me 8. Okay, so I'm going to use that command to define N for my calculation. Now we'll define delta. So delta is going to be equal to N times. Okay, now here's where we have to be very careful with our notation. The next term is the sum of the squares of x. So here's what I'm going to do. I'm going to sum x, and I'm going to square that. And then I'm going to subtract the sum of x squared. Okay? So this is now delta. And now the output still shouldn't really give me anything, but it won't give me an error as long as I haven't made a syntax error. And if I want to print what delta is, I can tell it to do that. And come back here and compare. If I actually calculate the same value here, what do I get? So remember that this was going to be n times the sum of all of x squared, and I'm going to take this and subtract this, and 336.0, and that's what we get here. So our code is on the right track. Our code should be working. All right. So now we're ready to print or calculate the slope. Okay. So my slope, whoops, is going to equal 1 over delta times n times the sum of x times y minus sum of x times the sum of y. Right? And oh, where are we? Where is the error? Oh, I need a multiplication sign right here. There we go. That should do it. And sure enough, it did. It didn't complain at me. So now, if I want to print the slope, I should get 1.2464 or 1.246429. In fact, it'll be a much longer string of decimals, but that's what it should give me. 1.24642857, yada, blah, 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 blah. Really, I would, in most introductory laboratory cases, I would truncate at 1.24. Okay, but it got me the right answer, right? It got me the right answer. And the intercept, the equation for the intercept is given by this expression. So I'm going to take 1 over delta. I'm going to multiply that by the sum of x squared times the sum of y minus the sum of x times the sum of x times y. All right? Long expression. But these are the equations that govern the linear regression. Okay, this is how you find the slope and the intercept. And these equations are universal, by the way. Okay, even if you take errors into account, I need to be very careful on how I say that. That's not quite correct. So I'll leave that as a misspoken statement for the moment, and we'll correct it in the next video. But for the moment, when your errors are equal, okay, if you can assume equal amounts of error on each of your y values, then this is true. Okay, this is how you calculate the slope and the intercept. And there we have it, right? Let's make sure this was right. And sure enough, right, the intercept is 1 and 1.0. That's actually kind of surprising. This is a complete accident. I just put this data in off the top of my head and gave it some scatter. So this is a complete accident that the slope or the intercept is exactly 1. The equations, the document that I have here has a slightly different data set. The equations for the uncertainties are slightly different. Okay, and I will actually go through those in the next video. I will leave that here for now, so that way this is a more manageable watch, and then we'll add to this shortly. But this is how you do it, okay? So what you've essentially done, if you followed with me this far, is you've written a routine. You can put any X and Y data in here, and you can find the slope and the intercept. Okay? You can find the slope and the intercept. If you want to complete the routine, okay, if you actually want to complete it so you can actually see the result, what I would do, one way to do this is to say, okay, what is my model? Well, we know the model is the slope times your X values plus your intercept. So I'm going to create an array called model, and that model is going to be my slope times my X values plus my intercept. Okay? And so now what I'm going to do is plot my X and Y values as black dots, and I'm going to plot my model as a red dash. Okay, and let's actually as dashed lines. And now this should show effectively the same plot that I have here in Excel. It should give me my data points and the slope and intercept. So if I run this, what do I get? Oh, whoops, that's because this is intercept. And sure enough, there you have it, right? And my slope is printed, my intercept is printed, and my plot is here. And if you scale it, you would find that it matches this plot perfectly, right? The values match that plot perfectly. So this is what we call a routine. You can input any of your experimental data, and as long as your X and Y data have the same number of elements, this routine will work, and you will be able to determine the slope and the intercept. So I hope you have found this helpful, and we will see you in the next video.